So today, I would like to introduce the topic of smart contract security and dataset. In the mid-1990s, cryptographer Nick Szabo introduced the concept of smart contracts. His definition of a smart contract is: a smart contract is a set of promises specified in digital form, including protocols within which the parties perform on these promises. But the technology was not widely supported and used due to the mismatch of technical means and the immaturity of the online trust environment at that time. It wasn't until the advent of blockchain technology and the maturation of the Internet at the turn of this century that it became useful. As you can see, the birth of Bitcoin marked the age of Blockchain 1, and in 2013, Vitalik released Ethereum white paper introducing smart contracts and Ethereum virtual machines for blockchain, marking the arrival of Blockchain 2. Since then, the smart contract platform has become more and more important in computers, finance, and many other fields. Smart contracts have the advantages of low cost, ease of use, globalization, and high trustworthiness when comparing with traditional contracts. But with the birth of Ethereum, smart contracts and platforms themselves have been in the shadow of vulnerabilities and hackers. For example, in 2016, the DAO project on Ethereum was hacked and hackers directly diverted 3.6 million Ethereum tokens, accounting for one-third of the total project crowdfunding at that time. In 2018, a major security vulnerability similar to the BSC overflow occurred in Smart Mesh, resulting in the theft of over 140 million by hackers. In April 2022, hackers attacked the Beanstalk Farms project through a malicious code logic vulnerability, which ultimately cost the project about $182 million. In recent years, a large amount of research on the analysis and detection of smart contract vulnerabilities has emerged, but there has been no common detection tool and corresponding test dataset. Therefore, we decided to complete the work of dataset of smart contracts. Considering the large scale and wide population of the Ethereum, both the quality of users and contracts are influenced by the number of contracts. A significant number of beginners are using Ethereum to learn about blockchain-related content, and a large number of contracts with no real meaning are deployed for only practice or even scams. To ensure fairness and accuracy when comparing the performance of smart contract vulnerability detection tools, we chose the smart contract platform BSC and Polygon, which are second only to Ethereum in terms of total value locked by platforms, to provide two kinds of datasets with a total of 4 copies. After confirmation of the platforms, the first thing to experience in organizing data is data collection. We learned that Polygon Scan and BSC Scan, two third-party websites, provide APIs related to queries and data downloads for smart contracts. After a short period of extensive data testing, we found that the APIs of these sites had restrictions such as an upper limit on the number of operations, so we wrote specific crawlers scripts to obtain a variety of information, such as contract source code, from these two sites. Considering that the technical difficulty of deploying contracts is small and there will be contracts that are not deployed for the purpose of use, we also set the condition that the current number of transactions is greater than 1 to perform the initial filter. After about 6 months of collection, we eventually acquired 77,178 contracts. After the collection of data, the initial construction of the dataset is completed. The next step is to filter and clean the collected data. Through observation of Solidity contracts, we found that a significant number of contracts import third-party online security libraries, such as OpenZipLink, which will inevitably have an impact on detection efforts in offline environments. So, we performed text reading of all contracts and cleaned out all contracts that have imported third-party online libraries, which totaled 25,218 contracts, accounting for 33% of the total collected contracts. Before classifying the dataset, it is important to note that contracts written in the Solidity will fail to execute when running EVM because the soft compiler version in the environment does not match the version declared in the contract. We then processed to perform text reading of all contracts in the dataset and classified the contracts according to the Solidity version declared in it, dividing the dataset into 6 broad categories. We named our dataset Generalized Smart Contract Vulnerability Dataset, GSVD. After data processing, version 1 of the GSVD was created. This is the structure of GSVD. As for GSVD miner, our vision is to provide blockchain security practitioners with a class of real-world smart contract datasets containing typical vulnerabilities. When researchers want to test their algorithms or tools on real-world contracts rather than typical vulnerability example contracts, they can experiment on the GSVD miner dataset and get a result that has been tested with real-world vulnerabilities. They can also perform control variance tests in open-source tools that do not open test the dataset to compare the performance of their own algorithms or tools. As for GSVD major, it is used for big data analysis and experiment on contracts and platforms in real-world environments. A dataset that consistently integrates a large number of deployed smart contracts in real-world chains is of considerable relevance. When blockchain security workers come up with a set of smart contract-related series or develop a series of related algorithms, they can experiment directly on GSVD major to validate their series and algorithms. The first page shows the number and distribution of vulnerabilities in GSVD miner. The second page shows the number and the Solidity versions distribution of GSVD major. After creation of GSVD, we chose 3 detection tools to detect on GSVD miner to test both our dataset and the tools. In order to find the right detection tool, we have further investigated 3 tools based on the selection of ASAF, and the list as well as the details are summarized in this table. Considering that the versions of Solidity language and the subcompiler have been iterating at a high speed, we finally chose Slither, Manticore, and Mythril, 3 tools that have been kept up to date to perform the detection work on the dataset. We created 3 counter virtual environments in the same device to construct the running environments of different tools and conducted test experiments in turn. This table shows the labeled vulnerabilities detected in GSVD miner. As you can see, these 3 tools cannot detect all 9 kinds of vulnerabilities. For example, Slither cannot detect arithmetic, Manticore, and Mythril cannot detect denial of service, local balance, and token standard. These 3 kinds of vulnerabilities, which shows that the mainstream open-source vulnerability detection tools can only focus on some kinds of vulnerabilities because of their practical application scenarios and underlying technology, which leads to their inability to detect other kinds of vulnerabilities. In addition to the vulnerabilities we labeled in advance, these detection tools are also detected some unlabeled vulnerabilities in the miner dataset, and we made a count of the number of vulnerabilities detected, which are presented in this table. Out of the 9 different vulnerabilities detected, 3 tools show some degree of false detection. Besides, there were a large number of other vulnerabilities detected by these 3 tools, which were labeled as others and recorded in this table. Because of the presence of these 2 phenomena, there are some cells in this table where the data recorded also exceeds the number of vulnerabilities labeled. After accuracy testing, this table shows the execution of each tool. We can see that Slither is the tool with the shortest execution time, taking only 22 minutes to complete detection of 153 smart contracts into subsets of GSVD miner, while Manticore and Mythril take significantly longer, with Manticore, which uses dynamic symbolic execution technology, taking the longest time, nearly 43 hours to complete. When it comes to the future work, with everything going well, we plan to continuously update the contracts for both platforms in Phase 2, expanding the minor and major datasets after screening and cleaning. Besides, we have plans to expand other blockchain platforms that support smart contracts and use EVM in Phase 2. In addition to theoretical and software work, the subsequent phase of work cannot be carried out without better equipment. We are already planning to use a multi-core processor, large memory cloud platform as the execution platform for experiments and datasets, which will greatly improve the speed of dataset construction and experiment execution. This is the end of our work introduction. Thanks a lot. Have a great day.